Now, the other arrangement that resistors can be in is what's called parallel. So what this means, we've got our battery, and then the circuit has separate branches. So this just looks like a simple circuit, but then there's another branch and another branch. So that's what it would look like with 3, 4, you just keep going. So the current splits 3 ways, and goes through these 3 resistors. Now, think about what quantity will be the same for each of them. Well, wires, our ideal wires, have no resistance, which means our ideal wires are all at the same potential. So the potential here is the same as the potential here. Potential here is the same as potential here. Otherwise, that would violate conservation of energy. So if the potential here is the same as the potential here is the same as the potential here, that means that what quantity will be the same for each of them? Well, the voltage, or the potential difference, I should say, across each resistor will be the same. Right? So that means that we can say I1 R1 equals I2 R2 equals I3 R3. So all of the potential differences are the same. And that is also equal to the potential difference across the battery. Okay? And we can say that the potential difference across the battery divided by the equivalent resistance of the circuit, however, we don't know how we're treating this yet, but if we treat all of them as one resistor, like I said, we don't know how that's going to work yet, but if we were to treat them all as one resistor, then dividing by the equivalent resistance would give us the current through the battery. Well, the current through the battery forks, branches off 3 ways, so the sum of those 3 currents would be equal to the current of the battery. So the current running through the battery, well, I already said that, is equal to I1 plus I2 plus I3. And therefore, I battery, that's I1 plus I2 plus I3. And from this equation, we can see I1 is equal to the EMF of the battery divided by R1. And here we can see that the current 2 is equal to the EMF of the battery divided by R2, EMF of the battery divided by R3. So that is E times 1 over R1 plus 1 over R2 plus 1 over R3. And this is E divided by REQ, so the REQ is in the denominator. So just to go back to our original equation, this is E divided by equivalent resistance. So if we figure that out, 1 over equivalent resistance equals this stuff. So the equivalent resistance, it's actually easier to write. You have to take another inverse, so we can say that equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. In practice, it's easier to write 1 over equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. So this is how resistors add in parallel. Now, notice, just take a simple example. Say we've got a resistor of with resistance 2 ohms, one with resistance 3 ohms. Take 1 over 2 plus 1 over 3, and then take 1 over that, and we get 1.2 ohms, which is smaller than either of the resistances I started with, 2 and 3. So in parallel, when you arrange resistors in parallel, you decrease the total resistance. While when you arrange them in series, they're just adding, and so increasing resistors in series increases the resistance. Okay. So let's take an example here. Say you've got a circuit, 20-volt battery connecting the 3 resistors in parallel with resistances 12, 25, and 15 ohms, and we want to find the current flowing through the battery. Well, if we want to find the current flowing through the battery, we say that the EMF of the battery is equal to I times REQ, current flowing through the battery, times what single resistor would make the circuit function kind of the same way. And we know 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3, which is 1 over 12 plus 1 over 25 plus 1 over 15. So we do that 1 over 12 plus 1 over 25 plus 1 over 15. 1 over answer. And we get that our REQ is 5.26-ish. So then we plug numbers in. 20 is the current through the battery times this 5.26. So we take 20 divided by that, and we get that the current through the battery, it's exactly 3.8 amps. Okay? And we want to find the current passing through each resistor. Well, we know from before that the EMF of the battery is also equal to the potential difference of the battery is equal to the potential difference across each of the resistors. So we can plug numbers in. 20 is equal to I1 times 12, which is equal to I2 times 25, which is equal to I3 times 15. I just decided to call these R1, R2, R3. It doesn't actually matter which one you would call which. So I1 is 20 over 12. It's about 1.67 amps. I2 is 20 over 25, which is 0.8 amps. I3 is 20 over 15, which is about 1.33 amps. So we can figure out what's going on with resistors in parallel. We can figure out what's going on with resistors in series. Next class, we'll work through how to deal with combinations of resistors. You can see on this page. So there's two parallel branches here, but then this is in series, and we'll figure out how to break that down and work with more complicated circuits next time. Here's your homework, and that's all.